Welcome to Lecture 2. We ended off Lecture 1 by considering SAS code to fit simple linear regression. We've considered the example where we looked at the exam mark predicted from the average test mark of students. We made use of PROG-REG as well as PROG-GLM to fit these models. We can easily read the estimators for the intercept and the slope from the output results from PROG-REG. For instance, we can see here is the estimate for beta naught, the intercept, while the value over here is the value for the slope beta 1. Please make use of this template to give you corresponding positions for relevant results from PROG-REG. For instance, in this position over here, we can find the estimator for beta 1. The mean square error is given over here, and the t-value for testing hypothesis in terms of beta naught is given over there. Please use the different positions to identify the relevant results on your output. Here we get the estimated regression equation with an intercept over here, the slope over there, and with x then the test score. We can easily predict for a test score of 42, an exam mark. An expected exam mark can be calculated as follows. Using the regression equation, plugging in the intercept of 10.72 plus 0.87 for the slope approximately, multiplying it with an average score for the test of 42, we can predict the exam mark to be roughly equal to 47.37. It is important to check the assumptions for the simple linear regression model. In order to do that, we need to calculate the estimated residual values. The estimated residual values are obtained by subtracting from the observed y value the predicted value. The predicted value can be obtained by making use of the estimated linear regression function. We can use that then, for instance, to go and check if the constant variance assumption is relevant. We can also use that, for instance, to check for normality by making use of the Shapiro-Wilk test. Let's see how we can use the estimated residuals to check for constant variances. We consider the plot of the residuals against the values of x. We then expect the residuals to fall within a constant band about 0. This will be an indication that the variance stayed constant as the values of x increase. For instance, what we don't want to see is a situation where we have a large spread in the residuals for large values of x and a small spread of the residuals for small values of x. For instance, then we have this V-shaped type of graph, which will indicate that the variances are not constant. The variance is small for small values of x, and the variance is big for larger values of x, clearly against the assumption of constant variances. ProgReg produces standard graph output, which we can use to check the assumptions of the regression model. In the left top corner, the same graph is given as what we've considered on the previous slide. Once again, we see that the residuals follow a constant band, which is supportive of the constant variance assumption. We also see down here a histogram for the residuals with a normal density function plotted on top of the histogram. This seems to be reasonable then to assume that the data follow a normal distribution. More so if we check the normal probability plot, which is more supportive of the fact that the residuals are normally distributed. We can perform a formal test to check if the residuals are normally distributed. We first fit a regression model to the data using ProgGLM. We then output the residual values from that model. We input these residual values into a ProgUnivariate, and then we perform a normality test on the residual values. ProgUnivariate indicate to us then different statistics for testing for normality. The Shapiro-Wilk test statistic is equal to 0.96 with a p-value of 0.69, indicating that we cannot reject the null hypothesis that the data, the residuals, are normally distributed. The results from the Shapiro-Wilk test that the data is normally distributed is supported by these graphs which we've obtained from the standard ProgReg output. We need to check if our model is significant. When will a model not be significant? Let's consider a scatter plot with x over here, y over there, and observations scattered as follows. Looking at these observations, it seems like that a regression line will be a line like this. Most likely a horizontal line implying no slope, meaning that beta 1 equals 0. If beta 1 equals 0, it implies that there's no association between x and y, and we then cannot use x to predict y. In which case we have an insignificant model. A significant model will be the case when beta 1 is not equal to 0. So it is important for us to test the hypothesis beta 1, or the null hypothesis, is equal to 0 versus an alternative hypothesis which states beta 1 is not equal to 0, in which case we'll have a significant model. For that, we need distributional properties of the estimator beta 1, and we also need distributional properties of S squared, and then we also need to know if beta 1 and S squared are independent. From this, which we will prove, from these results, which we'll prove later on in chapter 7, we will be able to calculate test statistics to test the hypothesis if we have a significant model or not. To test the null hypothesis that beta 1 equals 0, we will use the test statistic T, which follows a T distribution with n-2 degrees of freedom. Using this T statistic, we can actually test the hypothesis H naught beta 1 equals 0 against the alternative that beta 1 is not equal to 0, implying that we have a significant model. We can also use this T statistic to construct a confidence interval for the beta 1 parameter. The confidence interval is given by this equation over here. Please work through example 6.3 in example C1 to see how you can use the test statistic T to test the null hypothesis that beta 1 equals 0, or how you can go and calculate confidence intervals for the parameter beta 1. Once again, we can make use of software to help us to perform the hypothesis test. Here on the slide, we have the output from a ProgReg. We see here that the T statistic is actually calculated for us to test the hypothesis that beta 1 equals 0. The test statistic T over here equals the value 8.8 in the output. Associated with this T value is a p-value of less than 0.0001, implying that we can reject the null hypothesis and that beta 1 actually is significant different from 0. The results from the previous slide is once again summarized on this slide. Once again, we test the null hypothesis that beta 1 equals 0 against the alternative hypothesis that it's not equal to 0, taking alpha to be 0.05. Since the p-value is very small, which is less than the alpha value of 0.05, we can reject the null hypothesis and conclude, therefore, that the slope with a value of 0.87 is significantly different from 0 at a 5% significance level. We also see on this slide an example of a confidence interval calculated for the parameter beta 1. Please remember that the value over here is equal to the square root of the variance of beta at 1. Using that variance of beta at 1, we can then go and calculate a confidence interval for beta 1. We see that this confidence interval starts at the value of 0.6 and it goes to a value of 1.08. This confidence interval does not include 0, which also therefore indicate that we can reject the null hypothesis. We saw from the introductory slides that a certain proportion of the variance of y is explained by x through the regression function. The coefficient of determination quantifies this proportion of variation explained. In order to calculate the coefficient of determination, we need to calculate the sum of squares total, the total sum of squares, SST, which is also referred to as the total variation. The total variation can be explained as well as there's a component which is unexplained. To understand the concept a little bit better, we can look at the following graph. Let's put x over here as usual, y over there. And let's say the average of the y values are given by that horizontal line. Let's say that is our regression function, or our regression line. And let's say we have an observation over here. We can then see that the distance from the average, because we need to look at these deviations, that the distance from the average to the value of yi can actually be split into two components. The regression line splits this distance into two components. It's the portion which we call the explained component, the distance all the way up to the regression line, and the remainder, which is then the unexplained component. The coefficient of determination is then calculated as follows. We use the symbol r squared to indicate the coefficient of determination. It gives us the explained component as a ratio to the total sum of squares. This explained component is the sum of squares due to the regression, or the regression sum of squares, which is obtained by calculating the ratio as given. Please take note of the following properties. The fact that the sum of yi equals the sum of yi hat. That says the sum of the observations yi equals the sum of the predicted values of yi, which is equal to the n times the average of the y values. This can be obtained by the fact that the sum of these deviations which we've just considered equals 0. Please have a look and see if you can prove that the sum of the deviations are equal to 0. Also consider example 6.4, which is part of the broader example C1. From the PROC-REC output for the example of the exam marks predicted from the test marks, we see that the R-square value is 0.8288. That means that approximately 83% of the variation in Y is explained by the test marks. This actually indicates that the regression model is quite a strong model, since it's got the ability to predict 82% of the variation in the exam marks from the test marks. Please work through the next 4 slides. These slides give specific detail for example C. Please take note of the options in the model statement for PROC-REC. Also consider this extra question related to example C.